Om Swastiastu. Assalamualaikum warahmatullahi wabarakatuh. Salam nama budaya. Okay, in this video I will explain about chapter 8. But the first I want to introduce myself. My name is Putra Hutabarat with student ID number that is 23055311075. I am from Mechanical Engineering Study Program, Engineering of Fakultas Udayana University. Okay, Chapter 8, Steel Products and Properties. The purpose of this chapter is to introduce the various types of steel, compositional categories, and effects of alloying on properties. The main focus is on the key properties and products of carbon and low alloy steels, while tool steels and stainless steels are discussed in other chapters. Next, that's it. 8.1 Classifications of steel. Steels form one of the most complex group of alloys in common use, and there are many ways to classify steel. Classification of steel based on chemical composition is a widely used method. There are three very broad-based categories of steel based on composition. Feature 8.1 Plain carbon steel, low alloy steels, and high alloy steels, which include stainless steel. Next, steel making can be broadly classified into two steps: primary steel making in a converter or furnace, and secondary steel making in a ladle. Ordinary grades of steel may bypass the secondary steel making processes. The two most important steel making processes are the electric arc furnace EAF process and the basic oxygen furnace BOF process or LD Lins-Donowitz process. The EAF process accounts for 35 to 40% of the world steel production, and BOF produces 55 to 60% of steel. Solidification method. After steel is melted and refined, it is then solidified into usable forms by various casting methods. On a tonnage basis, most steel is now solidified in continuous casting operation, but casting of steel still involves the original method of solidifying into ingots. The molten steel is transferred from the steelmaking vessel to a refractory ladle, from which it is steamed into counter-ingots called ingot molds for solidification. Heat treatment. One of the primary advantages of steel is their ability to attain high strength through heat treatment while still retaining some degree of ductility. Heat treatments can be used to not only harden steels but also to provide other usable combinations of properties such as ductility, formability, and machinability. Next, 8.2 Carbon steels. Carbon levels have a pronounced effect on property. Picture 8.4. Carbon has very limited solubility in iron, and a hard carbide compound Fe3C called cementite forms when carbon is added to iron. The physical form of this carbide can be readily modified and controlled by processing variables with accompanying change in properties. The cementite carbides may be present as lamellate plates, needles, and spheres, or the carbon may be retained in supersaturated condition during quenching. which causes the formation of a very hard metastable base called magnetite. Medium carbon steels are similar to low carbon steels, except that the carbon range from 0.30 to 0.60% and the manganese from 0.60 to 1.65%, increasing the carbon content to approximately 0.5% with an accompanying increase in magnetite allows medium carbon steels to be used in the quench and tempered condition. The uses of medium carbon manganese steels include shafts, couplings, crankshafts, axles, gears, and forgings. Steel in the 0.40 to 0.60% Celsius range are also used for rails, railway wheels, and rail axles. Next, high carbon steels contain from 0.80 to 1% Celsius with manganese contents ranging from 0.30 to 0.80%. The microstructure is largely purolithic. They are used for applications where the higher carbon is needed to improve wear characteristics and where strength level required are higher than those obtainable with the lower carbon groups. Application includes spring materials and high-strength wires. Next, 8.3 alloy steels. Alloy steels containing manganese, silicon, or copper in quantities greater than those for the carbon steels, or they have specific range or minimums for one or more of the other alloying elements such as nickel, chromium, molybdenum, and so forth. Sometimes alloy steel are further defined as being either low alloy steel or high alloy steel, depending on whether total alloying content is less than 8%. Picture 8.1. This is not a hard and fast rule because some steels with alloying slightly above 8% are sometimes referred to as medium alloy steels. High alloy steels typically refer to stainless steel, maraging steels, austenitic manganese steels, and some ultra-high strength nickel steels. Next, high-strength low alloy steels are designed to provide better mechanical properties and or greater resistance to atmospheric corrosion than conventional carbon steels. They are not considered to be alloy steels in the normal sense because they are designed to meet specific mechanical properties rather than a chemical composition. They have manganese contents up to 2%, small quantities of chromium, nickel, molybdenum, copper, nitrogen, vanadium, niobium, titanium, and zirconium are used in various combinations. Quenched and tempered QT low alloy constructional low carbon steels combine high yield strength from 350 to 1035 MPa or 50 to 150 KSE, and high tensile strength with good knot toughness, ductility, corrosion resistance, or weldability. The various steels have different combinations of these characteristics based on their intended applications. Plate is a common product form, but some of these steels, as well as other similar steels, are produced as forgings or castings. In the terms of impact toughness, these steel generally outperform mild steel and HSLA steel at low temperature. Picture 8.5. Next, 8.4 Alloying elements in steel. Steel form one of the most complex groups of alloys in common use. The synergistic effect of alloying elements and heat treatment produces a tremendous variety of microstructure and properties. Carbon is the single most important alloying element in steel. It is the principal hardening element and essential to the formation of cementite, Fa3C, and other carbates, perlite, sphaerodite, bainite, and iron carbon martensite. The relative amounts and distributions of these individual pairs can be manipulated through heat treatment to alter the microstructure and therefore the properties of a particular piece of steel. Manganese is normally present in all commercial steels. It is important in the manufacture of steel because it deoxidides the melt and facilitates hot working of the steel by reducing the susceptibility to hole shortness. Next, silicon is one of the principal deoxidizers used in steel making. The amount of this element in a steel, which is not always noted in the chemical composition specifications, depends on the deoxidation practice specific for the product. Rimmed and capped steels contain minimal silicon, usually less than 0.05%. Fully killed steels usually contain 0.515 to 0.330% silicon for deoxidation. If other deoxidants are used, the amount of silicon in the steel may be reduced. Silicon has only a slight tendency to segregate. Hydrogen is an unwelcome alloy addition to any steel. It can be dissolved in steel during the melting and casting process through contaminate, scrap, or through water vapor and can seriously embrittle it. This effect is not the same as the embrittlement that results from electroplating or pickling. The presence of hydrogen can result in superface cracks or flake formation as the steel cools from hot rolling temperatures. Next, 8.5 Strength and toughness. Steel is usually associated with strength because in many of its uses it is necessary that steel, in one form or another, support a load. The bed spring supports the weight of a body, the car springs support the weight of the automobile plus the weight of the passengers, and the car frame must withstand extra forces due to acceleration and deceleration. A bridge must support the weight of cars, trucks, pedestrians, and the weight of the bridge itself. Toughness. Axle shaft and steering components of an automobile are examples of applications requiring toughness, because fracture of these components during service would be life-threatening. A large impact may bend the axle or steering components and make the automobile inoperative, but at last it is possible to come to a controlled stop. Next, the TBTT is strongly influenced by microstructural features such as grain size and paste constituents such as ferrite, perlite, martensite, or bainite. Finer grain size improves toughness and lowers the TBTT, while tempered martensite provides additional toughness at lower temperatures. Picture 8.8 Fatigue state. When a steel component is subject to repeat or cycling stresses, including vibratory stresses, the part can fail by fatigue even though the bulk stress levels acting on the part may be below the yield strength of the steel. For this reason, it is important to understand the factors influencing fatigue and fatigue resistance, and to be able to estimate safe stress levels for a part subject to repeat stress or strain. Next, the last, one of the most famous corrosion-resistant iron artifacts from antiquity is the Iron Pillar of Delhi, a 7-meter tall iron-based pillar that was constructed by the order of Kumaragupta I near 1400 A.D. It remains like this, picture 8.14, as a testament to the skill and ability of ancient Indian ironsmiths, and has attracted the attention of both archaeologists and metallurgists because it has withstood exposure to the elements for over 1,600 years without experiencing any significant section of corrosion. The pillar owes its corrosion resistance properties to its porous content, which results in the formation of a precipitation layer of iron oxides and phosphates on the surface. Okay, I think that's I can explain about chapter 8. If there are any error in reading, please forgive me, and thank you for watching my video. Thank you.